Hello, everyone. Let's work a little more on the review part of the statistical inference, meaning we learned about the confidence interval. Right now, we want to work on the hypothesis testing. So for hypothesis testing, it's very similar to the confidence interval. The concept is very similar. I'm going to show you quickly how we drew like the hypothesis tests and the test statistic that we work in the hypothesis testing from the confidence interval. Now let's look at the lecture notes. Okay. So suppose a reaction currently has a desirable yield of 70%, and we want to use a cheaper catalyst. But we are not sure that if it will give us the same yield or not. So we need to test it. So what are we going to do in the hypothesis test? In fact, we are defining two tests. The first one is that, okay, so the yield is going to be the same as 70%. We call it null hypothesis. Null hypothesis, we had it in the second year stats on chapter 8. I believe, yeah. So you can review it over there as well. Again, we have 4 cases, and we have like we define the 2 different tests, like hypothesis tests for it. So the null means no effect. It's like that. You don't need to add anything to your system. You don't need to go grab data to prove it. It's like that. Collect many data to prove it. You don't need to do any add anything to your system. For example, here, yield is like desirable yield is 70%. So we would say our null hypothesis, it's that when we prove it that the mu null is equal to 70%. And the next thing that we have, like the next hypothesis that we would have is alternative hypothesis. And alternative, you can see here is written an alternative, is like that. We want to prove it that if the mu null is not equal to the 70%. So for proving, for finding out the mu null is not equal to the 70%, what would we need to do is that we need to gather data. So to test this, we could collect a random sample of yield data using the new catalyst and determine if the sample mean is different from the 70%. We want to know that if mu null is not equal to the 70% or not. But the next question that when we say that is different from 70%, so how different is different? So with the hypothesis testing, we are going to answer that. So we say that with the alternative hypothesis and defining the null hypothesis of the mu null equal to the 70% and alternative hypothesis of mu null is not equal to the 70%. So for the alternative hypothesis, we would call it with H1 or HA. In some books, they use it H1, some books HA. It doesn't matter. I use H1 most of the time. But if you write down HA, I would consider as alternative hypothesis. So we could reject the null hypothesis if, for example, a 95% confidence interval calculated for the new sample mean does not include that 70%. So it's like that we need to know that what's the range for the confidence interval that we have when we want to define the hypothesis test. It's like that. Look at here. This example, it was like, because we didn't say anything about the variance of the population, and we were interested in the mean, so we would consider it as case 2. So you can see that in case 2, we were working with the t-table. So we say mu null. This is the definition of the confidence interval. I want to show you the connection between the confidence interval and the hypothesis test. You will see that quickly. Just the starting point is different. So with the confidence interval, we are starting with defining the confidence interval, like the interval, but with the hypothesis test, we are going to work with this, we call it test statistic. We are going to start with this test statistic. Now let's look at it. So we say mu null is between like x bar plus margin of error. So here the margin of error is the value from the table, like t table, times the standard error, and the standard error here is a s over a square root of n, and then that's the upper bound. The lower bound is going to be x bar up from the sample minus t, like we would choose t table, some number from the t, because we're on case 2, right? And then t times like the standard error, which is s over square root of n. And here we are just playing a little with it, like with the you would put the x bar, both sides has x bar, right? So put the x bar inside, like between two inequality signs, and then we can move the s over square root of n as well. That's for the standard deviation, because standard deviation is the positive number, right? It's the square root of variance, so it's positive all the time. A square root of n is the sample size, so it's a positive number as well. So simply we can divide it, all three parts, like this part and this part and this part, we divide it by the s over square root of n. So you will have that like minus t and positive t, right? And then you would have a number, like you would have a new number between these two ranges. So this new value that we find, like mu minus x bar over s over square root of n, if we rewrite, like play with it a little and get the absolute value of it, so you can write, because it has the absolute sign here, we can write down x bar minus mu over s over square root of n. You can write it mu minus x bar as well, it doesn't matter. The only thing is that when you look at it like this, probably it's going to remind you of something. This is the value for t. So we said that for case 1, when we wanted to transfer the numbers to the z word, like standardizing that in the z one, we said that is x. If it was x bar, it would be x bar minus mu divided by the standard error of that one, right? Which was the sigma over square root of n. And then we said that that was z equal to that one. If we were working with the x, not x bar, in that case, z would be equal to the x minus mu over a standard error of x, which is like the same as the standard deviation. So here, because it's case 2, t is going to be equal to x bar minus mu. And look at here, the variable is x bar, it's not x. So because of that, the standard error of x bar for case 2 is going to be s over square root of n. So we call this one test statistic. It's very important in hypothesis test that for each case, we would know that what is the test statistic of that one, and for that specific case. Then we have one sample. So for case 1, the test statistic is going to be x bar minus mu over like sigma over square root of n for one sample. If it's 2 samples, it's going to be different. So we are going to work on the 2 samples here as well. When it's case 2, you can see the test statistic is going to be this. So we can go one step further. The last line is true if 70% is a reasonable value for the mean yield in light of the data. So you can see that it's like that. This last bullet point, it's a definition that we use in the hypothesis test. So therefore, we can say if this test statistic that we found, it's greater than t, the t value that we read from the table. T is the symmetric, right? So the positive and negative is going to be the same. It's just a sign that is different. We would reject the null hypothesis of the mu equal to 70% and conclude that the new catalyst has indeed changed the yield. So what's the main point when we are working with the hypothesis testing is that we are looking to reject the null hypothesis. So we never can say that we just test a statistic. We never can say we accept something. We always reject. We reject the null hypothesis, or we fail to reject the null hypothesis. We're going to work on that. The above procedure has the important property that we carry out the hypothesis test at a 95% confidence interval. So there is a 5% chance that we wrongly reject the null hypothesis. And the reason that we say that it's a 5% chance is like that we said that we have 95% of the confidence interval, right? So there's a 5% chance that we would wrongly reject the null hypothesis, like that we have the yield inside it, but it's gonna, we are, by mistake, we think that we are in that area. So we call this one type 1 error. If you go back to the second year study, you will see that we talked about the type 1 error and type 2 error a lot. For now, just know that the type 1 error here is a 5%. Like by mistake, it's possible that we would wrongly reject it, or by mistake we would reject the null hypothesis. I can show you let me see if this is the last, yeah. I can show it on the board. Let me get, where is the marker? So here, look at here. And let's say it's symmetric, and when we are working with case 2 or case 1, T and Z, they are very similar. The only thing is that with T, we need to know that we consider them sample size as well. So when we are looking for the 95% confidence interval, so far we said that this is our confidence interval length. And here it's, if I'm working with if I'm looking at the 95% confidence interval, it means that this area under the curve is 95%. Like we are going to have 95% of the data points in this area, right? And the mu is going to be in this range as well. So that's what confidence intervals tells us. So when I say that 95% is here, it means that, okay, if I'm looking for two-sided, this one is two-sided. So it's like that half of the alpha is going to be here and half of the alpha is going to be here, which is, if we add them, is going to be 5%. So this 5%, we call it like that's the type 1 error, or it's like that it's possible that we wrongly reject the mu when the mu is in these two sides, right? So because of that, if you look at the type 1 error in the previous, like chapter 8 of the CHE 220, you will see more information and you will see examples of it as well. But the reason that we call it like, if you want to, we call it type 1 error, is that these parts are the alternative hypothesis. So we said that mu null is equal to 70% is like this area. Let me get another color. So this area that I have here, like this 95% that we would say, I would say mu is in this range, right? So I call this one that here I have the null hypothesis. These two areas is representing my alternative hypothesis. I'm going to go back to this figure later as well, but now let's go back to our notes. Okay, so here we have we would say that when we want to, we are going to find out the two borders, and we will see that if we are in this section or not. Now we can have the two-sided test or one-sided test. When we say two-sided or two-tailed, it's like that we would say our alternative hypothesis is that mu is not equal to 70%. So it doesn't matter if we are in this area or in this area. Mu is just not equal to the 70%. And when we say mu is equal to the 70%, be careful with this one. I've seen this mistake over time a lot. So it's 70% plus minus margin of error. So here, this CI, we would say we have our mu here, plus minus margin of error, right? So this area and this area is our margin of error, or our error, like general error. So when we say that mu null is equal to 70%, in fact, we say that mu null is equal to 70% plus minus that margin of error. But we don't write it down while we are writing down, like we make it like in the shorter version. If it was one-sided, so all the alpha would be in one side. We have an example in like on page 51, on the next page. So we will work on it. So we would say we have everything on one side. So mu is going to be greater than 70%, or mu is going to be less than 70%. And we talked that in the summary session last time. It depends on the experiments that we are working on. We can have the one-sided or two-sided. Okay. So look at here. This is a two-sided. So mu null is like that. We would say it's when we want to draw it, it's going to be very similar to this one that I have on the board. So you would have half of the alpha here and here. The next one is that one-sided with the greater sign. So when we have one-sided with the, like, you want to say that your mu null is greater than some value, like greater than 70%. So in that case, what are you going to do? You're going to draw a line here. So all the alpha is going to be on your right-hand side. And you would say that your mu is greater than some value. For this one, like for this, when we have like greater sign for this, like mu is greater than some value, we would call it right tail test. And for when we have one-sided like this, we would have, we would say our mu is less than some value, like less than 70%. So what are we going to have, how would we work with that is like that we're going to have everything on the left side of the figure. So we would call it left-tailed test. Let me see. We can draw it like, we can have it on the table as well. So we can say, let me show you on the table. It's not that idea. So this one was that when we had the two-sided. So what would we write down here? We would say mu for the as alternative hypothesis, mu is not equal to the 70%. Like 70% yield. This 70% can be 5, 6, 7. It doesn't need to be percentage for sure. So that's the two-sided. Let's look at the one-sided. For the same example, so let's look at here like this. And I'm looking for a situation that my mu null, my H null tells me that mu or mu null is equal to the 70%. And my H1 or alternative hypothesis is that their mu is greater than the mu null is greater than the 70%. So for this one, when we have it like this, what's going to happen is that we will say, okay, because we said that the 70% is this area, right? So the whole alpha is going to go to one side. So this is all the alpha, like 5% alpha. It's not half of the alpha. The alpha is going to be will go to the one side. And it's very similar to the one side or one tail of the confidence interval. So we would say that we would draw it like this for a situation like mu null is greater than some value. So you can see that the mu null is greater than this value that we would have here. So for this one is on the right. So I'm going to call it right tail. Or right-sided. So instead of having like it's one-sided, but it's a right-tailed one. We would have the reverse, like this mu null is going to be less than 70%. So all the alpha would go to the other side, and we would call it like the left-tailed. One-sided again, but the left-tailed. So that's the. Let me share my screen again. For the one. Okay, so it's for the one side of the greater sign and the when we have the greater or smaller.